Hello, this is my assignment one video for practical one, modern and industrial control. So here we can see my circuit for the temperature controlled system. Here is my Arduino Uno. I have connected an LED over here to monitor the pulse fluctuation of the relay. It's just so that I can visualize on and off. Here we can see my LM35 connected to the Arduino. We can see the bulb and we can see the relay. If I turn on my AC 220 volts, we can see it turns on, and I shall move on to the Simulink next. Over here, my Simulink model can be seen. So this is my Arduino block. It reads the sensor data from the LM35 and it applies the gain, which basically converts the voltage into actual degrees that can be displayed over here on the display block and can be graphed via the scope block. And then I just saved it into a variable that I can use later to plot the graph. Over here we have my pulse generator sending an on and off signal to the pin 9, which the relay is connected to, and I can again scope it. And lastly, time, I just save the time progression to a variable so I can generate various different graphs. Over here is my step response. As can be seen, it was all over the place at first, but eventually it became a bit steadier here at the end. I wanted to show the entire progression from t equals to 0 till t equals to 250 seconds. So the progression of the temperature across that time frame can be visualized. Over here is the improved modeled version. This isn't the real version. However, it's the approximated ordinal differential equation that I constructed. As can be seen, it's much smoother and reaches steady state in a much quicker fashion compared to the real data values. Okay, so what are the main factors that contribute to the differences between my ideal model and my realistic version? So number one, we have sensor noise. The LM35 produces small voltages which affect the system. Number two, nonlinear heat transfer. Small heat convections are generated which are nonlinear, and that affects it as well. Number three, we have ambient temperature variation. Since the room temperature is constantly changing, there will be heat loss. Number four, we have bulb filament dynamics. The resistance of filament changes with temperature, and as well as the fact that the temperature sensor isn't touching the filament directly, but rather touching the bulb covering. So there is a change in temperature in that regard. And number five, thermal lag between filament and sensor. Those are, I would say, the main five. I just added a few more. For the next section, I went over here to system identification and I used MATLAB to help me generate these graphs. So number one is the transfer function model, and as can be seen, it smoothens out the graph, but it's less realistic. And number two is the nonlinear ARX model, which basically reduces the noise a bit and smoothens it out. However, it's more realistic compared to the transfer function model. Lastly, here are my PI and PID controllers. So essentially, the P controller produced a relatively fast response. However, it exhibited a steady state error and did not fully eliminate all the offset, right? But then when I used the PI controller, it successfully eliminated the steady state error due to the integral that's been used. But this was accompanied by some slight overshoot. So I used the full PID and I combined the proportional gain, the overshoot elimination, and the stability from the D value, and this produced the best result.